For nearly a week before December 10th, 3 Atlas had moved with a kind of eerie silence through the space between Jupiter and Earth. The object had been stable, quiet and predictable, its trajectory untouched by any obvious disturbances. No major flaring events, no unexpected deviations, no signals or reflective pulses. It was, by all visible metrics, behaving like a passive interstellar traveller coasting on momentum alone. Telescopes around the world had settled into their daily rhythm of monitoring, collecting data, but not expecting much. What made this phase remarkable was not what was happening, but what wasn't. Interstellar comets, particularly those nearing planetary orbits, tend to become erratic. Whether it's solar heating, spin-driven gas release, or the gravitational tug from nearby objects, motion almost always becomes noisy. But Atlas defied that expectation. Its spin remained consistent. The coma, what little of it existed, showed no significant asymmetry. The dust tail, while faint, retained a linear structure. Even radio observatories picking up low-frequency background signals recorded nothing unusual. Atlas, by all definitions, was inert. Then came the flicker. At precisely 0642 UTC on December 10th, infrared sensors at the Cerro Tololo Inter-American Observatory picked up a sudden increase in mid-band reflectivity from 3I Atlas. It wasn't a flash, not a flare, just a step change, subtle but undeniable. A small spike in brightness, focused specifically in the 10-micron band, typically associated with thermal reflectivity or sudden surface rearrangement. This wasn't expected, not at this point in the journey, and not from a body that had shown no signs of instability. At first, analysts dismissed it as noise, perhaps a transient atmospheric distortion or a calibration error. But the reading was confirmed independently by 2 other observatories within minutes, one from Australia, one from Hawaii, 3 separate instruments, 3 different latitudes, all reporting the same anomaly. The flicker was real, and it didn't fade. Instead, the elevated brightness held steady, forming a new plateau in the object's light curve. It was like something had changed, permanently. Not a passing effect, not a rotation event, a transformation. The surface of Atlas, or at least a portion of it, now behaved like it had been reoriented or exposed. It wasn't scattering light like rough, dusty ice. It was bouncing it back cleanly, directly, like a mirror aligned with the sun. This was not something you see from ice or rock. The first theory to emerge was surface shedding. Maybe a dust layer had fractured, exposing a fresher, more reflective region underneath. But if that were the case, you'd expect a debris trail. You'd expect an increase in outgassing. You'd expect a shift in spin or a flicker in the coma. None of that happened. The tail remained steady, the spin signature unchanged. No dust plume, no shock halo, just light, and not just any light. The spike was tightly banded, thermally clean, and lacking the spectral chaos that usually accompanies mass ejection. It looked, in the data, almost artificial, not in origin, but in structure. Like a flat, angular surface had rotated into view. This is where the experts began to whisper. Because objects in space don't just change reflectivity patterns on command. They fracture, they vent, they erupt. But they don't smoothly shift into higher luminosity states without energy input or structural motion. And yet that's exactly what Atlas appeared to do. Over the next half hour, astronomers began revisiting old data, rechecking models, aligning orbital paths. One variable kept reappearing: Jupiter. Not its gravity, but its magnetosphere. Atlas had passed through the edge of Jupiter's magnetic influence less than 12 hours prior. No one thought much of it at the time, but now that intersection felt less coincidental, because right after exiting Jupiter's invisible field, Atlas lit up. And what began as a quiet flyby suddenly looked like ignition. What set this event apart from so many others in recent observation history wasn't just the flicker itself, it was the persistence. In space, brightness events usually behave like waves: sharp increases, rapid fades, brief anomalies smoothed out by time. But with 3I Atlas on December 10th, that wasn't the case. The light didn't fade, it held. And in doing so, it introduced a question that hung heavy in every observatory room. Why? By 70 UTC, astronomers confirmed that the infrared spike from earlier that morning had not only remained but stabilized. The object's surface was now emitting or reflecting at a constant rate. noticeably brighter than the baseline from the day before. That new plateau in brightness wasn't an echo or an illusion, it was real. And it didn't shift with rotation or wobble with thermal stress. It just held its line. Several things should have happened at this point, things that didn't. First, if the surface had fractured to expose reflective ice, thermal response curves should have shown a decline in temperature as the energy reflected rather than absorbed. But they didn't. In fact, the object maintained its temperature across all detected bands, suggesting that the brightness wasn't just a mirror effect. Something deeper was at play. Second, astronomers expected a fragmentation cascade. This is common when comets suddenly change luminosity, shedding pieces, dust clouds forming, or volatile pockets erupting under pressure. None of those signatures emerged, not even subtle signs. The tail remained linear. No debris field, no spin disruption, no vented cloud trailing behind. It was as if Atlas had entered a new mode entirely, as calm and deliberate as a machine powering up. Even stranger was what came from polarization data. As light scattered off the object's surface, instruments recorded an unusually narrow polarization curve, suggesting not chaotic particles but a smoother, more compact surface. It was reflecting light in a way more consistent with solid, engineered materials than porous cometary ice. As the day progressed, researchers across 4 continents began comparing readings. The brightness curve, usually spiky and volatile for active objects, had become flat. Not dull, but even, like a surface designed to bounce back radiation cleanly. And it wasn't dependent on angle. Observatories located at different latitudes, with different viewing perspectives, all saw the same thing. This wasn't a coincidence of angle. It was intrinsic. At this point, the speculation began to escalate. Could this object be reflecting in phases? Was there something on its surface reacting to solar radiation, opening, rotating, or energizing in response to proximity or light intensity? That would explain the sudden shift and sustained output, but not why it appeared so synchronized. And then came the comparative data, against 1I Oumuamua and 2I Borisov, the 2 prior interstellar visitors. Neither of them had exhibited anything like this. Oumuamua had been flat and fast, but dim. Borisov behaved like a traditional comet, but 3I Atlas was now emitting light in a way that was steady, unusually consistent, and bizarrely smooth. Too smooth for anything naturally rough, broken or irregular. There was one more layer that unnerved researchers the most: the timing. This shift in brightness occurred within a narrow window, after the object crossed Jupiter's magnetic boundary, and before it entered Earth's observational apex. It was almost as if Atlas had responded to something, ignited on cue, and was now in an active state. Was it residual heat? Unlikely. There was no corresponding thermal curve. Was it solar reflection? Partly. But that didn't explain the polarization or the longevity. Was it artificial? No one dared say it aloud. And yet, the fact remained. Atlas had changed. Visibly. Quantifiably. And it was holding that change like a command had been executed and confirmed. It was still bright, still stable, still silent. But that silence no longer felt passive, it felt prepared. By late morning on December 10th, the attention of every major solar and deep space observatory had fully shifted to one detail: the tail of 3I Atlas. Because while the object's core remained steady, the tail was no longer following the expected patterns of cometary physics. It had reorganized, visibly, structurally, and not by accident. Normally, a comet's tail is shaped by a simple interaction. The sun emits energy and charged particles, which strike the volatile materials on the comet's surface, vaporizing ice and dust and forcing that material outward. The result is a flowing stream of dust and gas, typically trailing away from the sun. That tail bends, curls, and shifts as the comet moves along its orbit. Solar wind sculpts it like smoke through a crosswind. But what appeared behind 3I Atlas defied all of that. Instead of a diffuse fanned-out cloud, observers now saw something different: structured filaments. Not random jets or irregular plumes, but clean, symmetrical V-shaped streaks, each extending hundreds of thousands of kilometers into space and tapering into precise lines. These weren't natural curls of dust being pushed by the sun. They looked like the aerodynamic wake behind an engineered vehicle. The comparison wasn't metaphorical, it was visual. The tail had shape. It had discipline. One of the first to notice was a researcher at the European Southern Observatory, who submitted a preliminary report noting that the tail was collapsing inward, not flowing outward. That phrasing would be repeated across multiple agencies by the end of the day. Images taken by ESA's solar orbiter revealed that instead of the usual outward streaming motion, particles were moving toward a central axis. Something was drawing them in, or, perhaps more unsettling, something was ejecting them in a guided pattern. This led to one of the first major questions of the day. Was the tail being formed by external pressure or by internal propulsion? If the former, then we were witnessing an unknown interaction between the sun's solar wind and the object's potentially conductive surface, something that might deflect or reorient charged particles in ways not previously observed. If the latter, then it wasn't just a tail, it was exhaust, directed energy being released from within the object, shaping the tail not as a byproduct of melting, but as the result of purpose. Simultaneously, ground-based spectrographs in Chile and Japan began detecting faint polarization differences along the edges of the tail, another oddity. In a traditional comet, the tail grows weaker and more diffuse the farther it extends. But with Atlas, the outer edges of the V-shape glowed more intensely than the center. This implied some form of lateral movement, almost like collimation, where particles weren't scattering randomly but were being channeled along defined pathways. And then came the strangest detail of all. The base of the tail, where it met the object, wasn't centered on the sun-facing side as expected. It was offset, slightly lower on the object's southern axis, and tilted at an angle that didn't align with the solar wind vector. That offset held steady across multiple hours and different telescope arrays. It was as if the tail wasn't reacting to solar conditions at all. It was responding to its own orientation. This behavior is unheard of in known comet science. Even the most active, unpredictable comets follow the basic principles of tail formation: heat, pressure, and dispersal. But 3i Atlas was doing something else. It was emitting material along a stable angle, in a clean formation, with no visible turbulence. There was no flutter, no warping, no deviation. The tail wasn't random anymore. It was symmetrical. It was active. It was behaving like a system. And in that silent geometry, the nature of this object shifted again, from passive to precise, from reaction to intention. Whatever was reorganizing that tail was doing so with purpose. As Earth's observatories scrambled to process the unfolding ignition event around 3i Atlas, one of the most unexpected data points didn't come from the object itself. It came from Jupiter. More specifically, from deep within Jupiter's magnetic field, a region so vast and complex that it extends millions of kilometers into space, forming the largest planetary magnetosphere in the solar system. And on December 10th, something inside that magnetic field echoed. Roughly 12 hours before 3i Atlas ignited, magnetometers aboard the Juno spacecraft, orbiting Jupiter at the time, registered a localized pulse, a brief compression in the outermost boundary of Jupiter's magnetosphere. It wasn't large enough to suggest a solar event. It wasn't directed. It was internal. An almost imperceptible ripple, like a muscle twitch in the electromagnetic body of the gas giant. At first, this data was background noise. Jupiter's magnetosphere constantly shifts, sometimes from internal dynamics, sometimes from interactions with its volcanic moon Io, which spews charged particles into the surrounding plasma. But this time, the pulse came from a direction not associated with Io, Ganymede, or any other known interacting object. It came from open space. And the direction of that anomaly? Precisely along the incoming vector of 3i Atlas. The alignment was too precise to ignore. Scientists at the Max Planck Institute for Solar System Research ran a simulation, backtracking the object's trajectory and aligning it with the structure of Jupiter's magnetotail, the enormous stretched field that trails behind the planet as it moves through the solar wind. The simulation showed that Atlas passed directly through the edge of that magnetic boundary, not deep inside, but far enough to make contact with the Loeb's outermost field lines. That's when something strange happened. Within 2 hours of that magnetic crossing, Atlas began exhibiting subtle signs of internal heating, picked up by long-range infrared sensors, not explosive heating, not from solar radiation, but something more like induction, low-frequency build-up, a slow internal hum. The correlation raised immediate questions. Could Jupiter's field have triggered something dormant inside the object? Was this simply electromagnetic exposure, or something closer to activation? Historically, interactions between comets and Jupiter's magnetosphere are rare, and even when they occur, they're usually dominated by gravitational effects, course deflections, tidal disruption, or in extreme cases fragmentation. But Atlas was moving too fast and its path too distant for gravity to have played any meaningful role. This was not a gravitational anomaly, it was electromagnetic. Adding to the mystery, the frequency of the pulse matched a band that's rarely observed in natural resonance. It was centered in a range typically seen during artificial induction experiments, low, slow, and sustained. It wasn't the magnitude of the signal that startled analysts, it was the timing. The signal occurred before the visible ignition, but after Atlas had entered the field. That gave birth to a chilling theory. What if the object had been waiting? Not consciously, perhaps, not as if it were aware, but structurally designed to respond only once a specific field strength or orientation was detected. If that were the case, then the interaction with Jupiter's magnetosphere wasn't incidental, it was catalytic. Researchers studying interstellar physics began referencing an obscure term, resonant threshold. In theory, if an object carries a conductive material embedded in a specific geometry, it could respond passively to electromagnetic fields, much like a tuning fork resonates only with certain frequencies. If Atlas was composed of such a structure, even a brief pass through Jupiter's magnetosphere might have delivered enough energy to initiate change, and that change had a direction. The field pulse pushed outward from Jupiter, and the ignition followed, precisely aligned with the direction of exit, as if the object responded not by resisting the field, but by using it. Jupiter didn't ignite 3i Atlas directly, but it may have whispered the signal, and the object listened. As the ignition phase of 3i Atlas intensified on December 10th, instruments tuned to the object's emission spectrum began detecting an anomaly that would deepen the mystery further. It wasn't in the light curve, it wasn't in the tail, it was buried in the spectrum, specifically in the region around the jets now visibly extending from the body, and it told a story no comet had ever told before. From Chile to Hawaii, mid-resolution spectrometers began to register a distinct redshift in the material trailing from the southern arc of the object, just beneath the ignition halo that had formed hours earlier. Redshift, in simple terms, means light waves are being stretched, and in space that almost always points to motion, something moving away fast enough to shift its signature toward longer, redder wavelengths. But this wasn't a diffuse shift across the whole object, it was localized. Only the jet region, narrow, directional, and consistent. The rest of 3i Atlas held its spectral identity. The core stayed cool, the northern edge remained balanced, only the jets moved, and they moved in a way that made scientists lean in, then go quiet. Because redshift in a jet doesn't imply chaos, it implies precision. These weren't particles being thrown out by heat, they were being directed, they had velocity, and that velocity followed a fixed, stable path. One scientist described it as a traffic lane of light, and that wasn't far off. Spectral maps showed that the redshift wasn't just uniform, it was rhythmic. A subtle wave pattern could be observed in the emissions, like a pulse nested inside the shift. This meant one of two things. Either the particles themselves were being released in pulses, or the material was passing through a field that was modulating its motion after emission. Either possibility pointed to control, not randomness. The usual explanation in cometary science is outgassing. Ice vaporizes, gas expands, and dust is hurled into space along with it. This chaotic process usually leaves behind messy, wideband spectral lines, unsteady, uneven, and hard to track. But that wasn't what instruments were picking up. The spectral lines here were clean, narrow, distinct. They resembled what you'd see in the exhaust plume of a satellite, not a comet. This prompted a new line of inquiry. If this was ejection, what was the force source, not sublimation? That was ruled out by the lack of corresponding volatile emissions, not impact. There were no nearby bodies, and not gravity, since the object wasn't accelerating in a natural curve. It was holding trajectory, even while releasing mass at high velocity. That raised a troubling possibility. Was this an internal propulsion burst? And if so, What was powering it? The energy output implied by the velocity of the redshifted material was enormous. For a natural object to vent that much mass at that speed without heating up or fragmenting is nearly impossible. But 3I Atlas wasn't heating, it was glowing. There's a difference. The glow wasn't thermal radiation from stress, it was spectral emission from directed motion. Adding to the puzzle, the redshift was flanked by faint blue edges on either side, suggesting possible precession. As if the material wasn't just firing backward but spiraling, twisting. A corkscrew of energy released not in panic but in pattern. This behaviour had no precedent in known comet mechanics. Even hyperactive solar system comets, like Hale-Bopp or 67P, never demonstrated this kind of structured emission. Their jets were unpredictable, asymmetric, wild. 3I Atlas's jets were aligned, narrow and symmetrical, and they were moving faster than anything natural should, without disturbing the object's stability. That left scientists with one conclusion they didn't know how to name. The jets weren't just active, they were moving with intent. As the redshifted jets from 3I Atlas became impossible to ignore, a familiar name began to re-enter the scientific conversation, a name that had once triggered both curiosity and controversy. Avi Loeb, the Harvard astrophysicist who, years ago, argued that the first known interstellar object, Oumuamua, may have been more than just a rock tumbling through space. His theory, that it exhibited properties consistent with artificial propulsion, possibly solar sailing. At the time, it was dismissed by many as speculative, even irresponsible. But now, on December 10th, that same framework was being quietly reconsidered. Because what scientists were seeing in 3I Atlas didn't just resemble Loeb's predictions. It was in some ways a mirror of them, but on a more advanced scale. While Oumuamua displayed irregular acceleration with no visible outgassing, Atlas had just ignited in a structured fashion, deployed directional jets, and maintained a course with unnatural precision. And it had done so after crossing through Jupiter's magnetic threshold, triggering a cascade of anomalies. In other words, Loeb's solar sailing hypothesis was back, but this time it wasn't just sailing, the clearest sign was the velocity alignment. 3I Atlas's jet structures were not simply ejecting material, they were doing so at angles that aligned precisely with known vectors of photon pressure, essentially allowing the object to capture solar radiation and convert it into momentum. But unlike a passive sail, Atlas seemed to decide when and how to activate. This wasn't consistent with a debris fragment or frozen rock, it was conditional behaviour. That conditionality was the cornerstone of Loeb's earlier work. His hypothesis had always centred on one idea, that some interstellar objects might carry reactive components, mechanisms that activate under specific environmental triggers. A close pass to a star, a magnetic field intersection, a spectral alignment. These would not be signs of life, but of engineering, of systems set in motion long ago, travelling distances that no living thing could survive. Now, as data came in from NASA's Deep Space Network, the spectral echoes and rotational stability of 3I Atlas matched simulations first proposed in Loeb's original interstellar probe models. Specifically, the object's ability to maintain a tight, stable spin even while ejecting mass contradicted the basic laws of conservation of angular momentum, unless that momentum was being counterbalanced intentionally. Intent. That was the word no one wanted to say, but the math kept pointing in its direction. The synchronization between jet bursts and solar alignment was tighter than randomness allowed. The structural consistency of the tail defied natural variance, and now the thermal readings showed a surface temperature that not only avoided overheating, but plateaued, as if regulated. At the SETI Institute, several researchers began revisiting Loeb's earliest papers, comparing the observed data from 3I Atlas to the theoretical behaviour of an interstellar probe that uses solar energy not just for propulsion, but for decision-making. His models had always assumed that such a probe would wake up near a star, conserving power for millions of years, then activating once a local energy gradient became favourable. Jupiter's magnetosphere provided that gradient. The ignition was the response. Even those previously critical of Loeb's views now found themselves in private discussions about the possibility. Not because they wanted it to be true, but because the alternative explanations were falling apart. No sublimation model explained the lack of volatiles. No spin model explained the stabilization under thrust. No energy model closed the budget gap between solar input and kinetic output, and so Loeb's model didn't just reappear, it gained traction, not as proof, not as proclamation, but as the only framework that made the data stop sounding like a mistake. Because if 3i Atlas was reacting with conditions, if it was deploying jets with purpose, and if it was regulating its own structure through controlled surface events, then maybe we weren't just watching a comet evolve. Maybe we were watching a probe remember what it was designed to do. By midday on December 10th, as astronomers pored over the jet activity and mid-infrared emissions from 3i Atlas, a new structure began to emerge, one that didn't fit within any model of tail formation, outgassing, or magnetic field interaction. It appeared slowly at first, tucked within the jet zone, then widened and stabilized. A luminous curve of material suspended like a crescent around the object's forward trajectory. Observers began calling it an arc. Not a tail, not a plume, an arc. Unlike the usual chaotic blowouts seen from comets, where gas and dust stream away in loose directions dictated by heat and spin, this arc formed with deliberate geometry. It curved upward and outward from a fixed anchor point near the southern axis of the object, swept in a perfect parabola around its flank, and then dissipated evenly on the opposite side. The shape held. It didn't twist, it didn't fray, it didn't evolve into the chaotic spiral seen in typical rotational venting. It remained balanced, luminous, and utterly silent. And it didn't rotate with the body. That was the first clue that something very strange was happening. Tracking the arc over time, analysts noticed that it held its position even as 3i Atlas rotated beneath it. The core rotated, as expected, but the arc remained static, as though detached from the surface. That separation, physical or electromagnetic, suggested that this feature wasn't just ejected gas. It was organized plasma, magnetized dust, or some hybrid field-generated structure. Spacecraft telemetry from the Parker Solar Probe and ESA's Solar Orbiter, both observing the solar wind interaction zone nearby, began to show faint distortions in ion density, subtle bends and deflections in the solar flow that coincided exactly with the arc's location. In simpler terms, the arc wasn't just visible, it was affecting the environment. It behaved like a shell, not dense enough to deflect particles directly, but present enough to cause ripples in the solar wind around it. One theory emerged almost immediately: magnetic confinement. This would suggest that 3i Atlas had generated, either passively or actively, a field strong enough to contain ionized particles in a suspended crescent around its body. In Earth science, this is how plasma toroids are held inside fusion chambers, by using external magnetic fields to confine energetic matter without allowing it to touch a solid surface. If Atlas was doing anything close to that, it wasn't acting like a comet, it was acting like a machine. A more conservative theory suggested that the arc was a byproduct of sunlight, refracting off a recently expelled layer of microscopic dust. Fine particles launched in a controlled sheet, forming a temporary reflective field. But even this idea struggled to explain the arc's symmetry, and more importantly its stability. Any natural dust sheet would have broken apart within minutes under solar pressure. This arc had held position for over 3 hours, and there was another problem. The arc didn't align with the solar vector. If it was sunlight or pressure-driven, it should have formed opposite the sun, trailing behind the object. But this arc curved perpendicular to the direction of motion, hugging the forward edge like a protective brace or aerodynamic shield. That's when the term navigation envelope began to circulate in private analyst calls. Not publicly, not in papers. But behind closed doors, researchers began to ask if this arc was more than an artifact. Was it shielding, a control field, a structure designed to hold shape while guiding the body's motion? In visual overlays, the arc mirrored orbital lines, not of Atlas itself, but of the predicted acceleration vector recorded just after ignition. It didn't follow the tail, it led the motion, and in doing so, it changed everything. Because 3i Atlas wasn't just ejecting mass anymore, it was forming architecture. By the early afternoon of December 10th, thermal sensors trained on 3i Atlas began reporting an uptick that had not been anticipated. The object's surface temperature was rising, but not in the way comets usually respond to sunlight. This was not a chaotic thermal spike. It was controlled, gradual, layered, and most notably it came with no signs of associated mass loss. That broke the rules. In every known case of cometary heating, rising temperatures lead to one thing: sublimation. Ice transforms directly into gas, breaking free from the surface, forming a cloud of vapour and dragging dust along with it. As the heat builds, the nucleus vents violently, forming jets, comas, tails, and leaving trails of debris behind. But 3i Atlas was breaking the link between temperature and loss. Satellite sensors from both Earth orbit and deep space probes measured the thermal rise in 3 specific bands: near-infrared, mid-infrared, and sub-millimeter wavelengths. The increase was consistent across all instruments. No flaring, no volatility, just a slow, measurable warming over the course of 4 hours. It plateaued just above what any inert rocky body should experience at that distance, from the Sun. Yet every optical scan of the surrounding space, every radiometric probe aimed at the coma, and every spectrographic sample of the surrounding environment told the same story. There was no additional gas, no dust, no particles, no bloom of volatiles. Nothing was coming off the surface. The conclusion seemed impossible. The object was heating from the inside. That idea raised difficult questions because natural bodies don't work that way. Passive objects, whether comets, asteroids, or interstellar debris, heat from the outside in. Solar radiation strikes the surface, begins to warm the outer layers, and gradually works its way inward. But the temperature pattern of Atlas showed something inverted. The inner regions appeared warmer than the outer shell. Thermal inversion, in a free-floating body, is not a natural condition. The first hypothesis was thermal insulation. Maybe a dense outer crust was trapping heat below the surface. That might work for some icy bodies, like Europa or Enceladus, where surface layers act like blankets. But those are moons, stabilized by gravity and tidal heating. 3i Atlas is an interstellar object with no stabilizing body, no consistent rotation axis, and no geological cycles. It should not have a warm core, and even if it did, something should have leaked out. Heat has to go somewhere. When pressure builds, it vents, and yet nothing vented. So the next possibility was even stranger. Maybe the object wasn't storing heat. Maybe it was generating it. A few voices, quietly at first, began to suggest internal energy. Not in the sense of nuclear activity or radioactive decay. There was no gamma emission, no isotope trace. But perhaps stored energy from a previous encounter, magnetic, electrical, or otherwise, was being redistributed. In other words, what if 3i Atlas had captured energy during its pass through Jupiter's magnetosphere and was now activating it internally? That idea led researchers back to an older model, used not for comets, but for spacecraft: thermal regulation. Artificial probes are designed to store, manage, and redistribute heat in extreme environments. They absorb solar energy, convert it to electrical signals, and then dissipate it as needed to protect structural integrity. Could it be that Atlas was doing something similar? Not just reacting to the Sun, but regulating itself? Because that's what the data looked like. The thermal curve flattened at a level just below destructive stress. The object had stopped warming, despite still approaching maximum solar flux. It hadn't broken apart. It hadn't lost mass. It hadn't vented. It had stabilized. And in that stillness, a realization began to form. 3i Atlas wasn't just surviving. It was managing its exposure. Actively, not passively. Comets endure the sun. But this object was adapting to it. By the late afternoon of December 10th, the light signature of 3i Atlas revealed something that sent shockwaves through the astrophysical community. Not only had the ignition event remained stable, not only had its internal temperature risen without shedding mass, but now the traditional tail structure, the signature feature of any comet, had shifted dramatically. It wasn't the ion tail that drew the most attention. It wasn't the dust tail either. It was the anti-tail. And for the first time in recorded observation, it had become the dominant visible structure. To understand why that matters, one must first grasp what an anti-tail even is. In cometary science, the anti-tail is a rare optical phenomenon. It's not truly a tail in the physical sense, but rather an illusion of geometry. As a comet moves through space, it often leaves a trail of larger dust particles along its orbital path. From certain angles, particularly when Earth passes through or near that plane, those lingering particles can appear to stretch sunward, creating what looks like a tail pointing in the wrong direction. It's visual trickery, an effect of perspective, a mirage. But with 3i Atlas, this was no illusion. Telescopes from multiple vantage points, North America, Europe, and Asia, all confirmed the same structure, a dense, luminous projection pointing directly toward the sun. And it wasn't diffuse, it wasn't smeared or scattered, it was sharp, focused, active. The anti-tail wasn't a leftover, it was launching. This observation flipped conventional comet physics on its head. Dust and gas are supposed to be pushed away from the sun by radiation pressure and the solar wind. Tails point anti-sunward because that's the natural direction of force. Nothing in our models allows for material to stream in the opposite direction, unless that stream is being driven by something else entirely. And so, new models were drafted on the spot. Could this anti-tail be an actual exhaust vector, a form of directed mass ejection, used not to display activity, but to generate thrust? Because if that were the case, then 3i Atlas was no longer exhibiting comet-like behavior. It was exhibiting spacecraft-like behavior. One set of simulations tested the hypothesis. If the object were releasing mass sunward, Newton's third law would apply. For every action, an equal and opposite reaction. Expel material toward the sun, and the object gains velocity in the opposite direction. A sunward anti-tail then becomes a crude but functional propulsion mechanism. Not random, not reactive, intentional. And it wasn't just the direction that made this anti-tail different, it pulsed. High-resolution imaging from ESA's solar orbiter revealed intervals of brightness within the structure, spaced evenly, like the notches of a gear. Not flickers, not turbulence, regular spacing. That pattern suggested modulation, some underlying rhythm in how material was being released, almost like timing cycles, not unlike the pulse cycles of an ion engine. Further confusing the issue, spectroscopy of the anti-tail revealed almost no volatile compounds, no water vapour, no carbon dioxide, just faint traces of micron-sized dust and heavier organic compounds. In other words, not the kind of stuff you'd expect to see venting from a sublimating ice mass. It wasn't the material that was impressive, it was the direction. And now the anti-tail wasn't just visible, it was defining the object's behaviour. Every motion from Atlas was now oriented around this new axis, as if its entire posture in space had changed. The arc structure from earlier chapters began to shift slightly, following the anti-tail's curvature, almost as if the system was rebalancing around a new orientation vector. Within hours, scientific reports stopped referring to it as an anti-tail. They started calling it an exhaust line, and that semantic shift carried weight. Because if the brightest feature coming off 3i Atlas was pointing directly into the sun, defying both physics and instinct, then this object wasn't just igniting, it was manoeuvring. By nightfall on December 10th, spectrographs from both ground-based observatories and high-altitude balloon sensors started detecting something even more precise than the arc or the anti-tail. A rhythmic pattern in the Doppler shift of emitted material. At first, the data appeared noisy, irregular, perhaps even corrupted by interference. But after careful filtering and synchronized timestamp alignment, a consistent pulse began to emerge. It wasn't visual. It wasn't something that could be seen in photographs. It was something that could only be heard in the frequency of movement. The Doppler effect, the stretching or compression of waves based on motion relative to an observer, is a foundational tool in astrophysics. It's how we measure the speed of stars, the drift of galaxies, the flow of gas in planetary atmospheres. In comets, it's used to track jet velocities, rotation, and turbulence. But 3i Atlas wasn't just shifting in frequency, it was pulsing. Specifically, scientists observed alternating blue shifts and red shifts in the spectral lines associated with certain jet emissions. That suggested not random outbursts, but oscillations, regular movements toward and away from the line of observation. It was like watching the heartbeat of an object in space, and it happened every 17 seconds. The exact timing varied slightly based on the angle of observation, but once adjusted for perspective, the pattern held. A 17-second rhythm of motion, Not fast, not explosive, but consistent, predictable, measured. No known comet behaves this way. In natural outgassing events, material is ejected when pressure builds from internal heat. That pressure varies based on composition, location, solar exposure, and spin. It's chaotic, it's noisy, it's not rhythmic. There's no natural mechanism that could time the release of mass so cleanly, unless the system doing it had some form of internal feedback loop. That realization unsettled even the most conservative observers. What kind of object maintains that level of timing precision while travelling at interstellar velocities? What kind of structure could sustain the heat, the rotation, and still eject material in discrete pulsed events? One theory, revisited from early papers on spacecraft propulsion, focused on pulsed plasma ejection, a theoretical system where energy is stored and then released in bursts, creating tiny, regular thrusts to adjust trajectory or orientation. This has long been proposed as a method of deep space propulsion in robotic probes. But those ideas were speculative, unproven, prototypes never left Earth. Yet now something was doing it in space, right in front of our eyes. The Doppler pattern didn't just show directionality, it also hinted at energy consistency. Each pulse was nearly identical in speed and spectral width. That means the force behind each ejection was uniform, no variation in fuel composition or chamber pressure. That's not just rhythm, that's engineering. Even more curious, the 17-second cycle aligned closely with the previously detected modulation in the anti-tail structure. The intervals between pulses in the tail brightness and the Doppler shift of motion were perfectly correlated. That wasn't a coincidence. It was cause and effect. One controlled system, two outputs. The implications were staggering. If 3i Atlas was ejecting material rhythmically, affecting both its orientation and tail composition, then we weren't looking at an object riding through space. We were looking at one navigating it. Because randomness doesn't pulse, chaos doesn't time itself, and comets, no matter how wild, don't leave behind signatures that resemble clockwork. At the SETI Institute, one analyst made a quiet comparison. It's like listening to a beacon, not broadcasting information, just reminding the cosmos that it's still active. Others weren't ready to go that far, but no one denied what the instruments were saying. 3i Atlas had a rhythm now, and space was starting to listen. As December 10th drew deeper into night, one of the most anticipated developments in the behaviour of 3i Atlas never arrived. No matter how much it ignited, no matter how many jets fired, how much heat built, or how visible the anti-tail became, there was still one silent absence that dominated every observation report. The coma was not expanding. That quiet fact grew louder with every passing hour. The coma, in cometary terms, is the cloud of gas and dust that forms around a nucleus as solar radiation begins to heat and sublimate its surface. It's what gives comets their iconic glow. When material escapes from the core, it envelops the object in a shroud of haze that reflects light, alters its spectrum and, critically, grows the closer it gets to the sun. But on this day, something was fundamentally wrong with that process. From Earth-based telescopes to solar observatories in heliocentric orbit, instruments locked onto the outer shell of 3i Atlas, expecting it to swell. That's the standard playbook. As solar pressure increases, so does the rate of sublimation, which should create more gas, which should expand the coma outward in a measurable sphere. Instead, it held still. The coma remained razor-thin, densely structured, and most disturbingly, bounded. In fact, high-contrast imaging showed what looked like a sharpening at the coma's edge. Rather than softening as vapour escaped outward, the boundary remained crisp. Its edge didn't feather or diffuse, it traced a clear perimeter around the object, even as the internal brightness surged and spectral activity intensified, and in every observable metric, dust particle count, vapour concentration, photometric profile, the coma size stayed fixed. That shouldn't be possible. Natural systems don't self-contain gas clouds in space. There's no atmospheric pressure out there to hold particles in, no gravity well strong enough in a small object like Atlas to stop escaping matter. So once something vents, it drifts freely, diluting with distance. But not here. What the scientific teams observed was less like a natural coma and more like a containment envelope, a sheath of particulate matter that simply refused to expand, as if locked in by an invisible membrane. One astrophysicist from the University of Hawaii put it plainly, "It's not behaving like a gas cloud, it's behaving like a field boundary. If that sounds speculative, it's because it is." But at some point, observational facts begin to outpace conservative theory. And the fact was this. 3i Atlas had created an energetic, high-temperature event with sustained directional jets, rhythmic ejections, and still, its surrounding shell remained unchanged. No plume, no bloom, no spherical inflation. Some floated the possibility of a magnetically bound coma, a system in which expelled ions are held in shape by local magnetic loops or toroidal flows. This has been theorized for planetary aurorae or confined plasma in laboratory fusion tests, but not in the open vacuum of interstellar space, and certainly not from an object with no visible electromagnetic machinery. And yet, if such a field was in play, it would explain the eerie stability, the consistent opacity, the hard outline. It would also imply active management, because fields don't hold themselves. Later in the evening, one final comparison changed the tone of many private analysis groups. They reanalyzed early comet models looking for a precedent, and found one, not in natural comets, but in controlled gas retention systems on human-made probes, where material was allowed to vent in a controlled zone, held briefly, and then released in pulses. In those systems, nothing expands uncontrolled. Everything is managed, every release is planned, and suddenly, the silence around the coma wasn't just mysterious, it was deliberate. As observatories continued tracking 3i Atlas through the night of December 10th, another subtle shift began to emerge, not in brightness, not in mass, and not in tail length. Instead, the change came in directionality. Specifically, the jets now appeared to be aligning, methodically and precisely, to the object's orbital tilt. At first, this detail escaped notice. The jets, having already demonstrated rhythmic pulses and a surprising lack of mass loss, were assumed to be either random outbursts or sun-driven reactions. But frame-by-frame analysis revealed something no natural comet has ever shown. The jets were realigning themselves, not toward the sun, not away from it, but along a very specific inclination. They were matching the object's exact orbital plane. This behavior is foreign to natural physics. Comets vent in messy patterns. Their jets are dictated by surface fractures, rotation wobble, and patchy exposure to solar radiation. Even when they appear stable, it's usually due to spin synchronization or slow erosion, not calculated alignment. But 3i Atlas was now different. Over a span of 6 hours, its jet streams adjusted gradually, not chaotically. From a slight diagonal slant, they began tilting downward, toward the same plane on which the object was orbiting the Sun. More precisely, they were correcting their emission angles to match the tilt of the orbital inclination, which itself was just over 25 degrees relative to the ecliptic. That specific figure matters, because the orbital tilt of a body determines how it intersects with the planetary plane of our solar system. Most solar system objects align closely with the ecliptic, the flat plane in which Earth and most other planets orbit. But 3i Atlas does not follow that path. Its trajectory is inclined, sharp, slanted, entering at a steep angle from interstellar space, and now its jets were matching that angle. That means the emissions were not fixed to surface geography. They were not erupting from static points on the crust. They were tracking something more abstract, an external orbital coordinate system, as if the object was aware of its path and adjusting its emissions accordingly. This was not random outgassing, it was vector correction. Several teams proposed simulations. What would happen if the jets were used to maintain a perfectly inclined trajectory? If the object were encountering drag, solar wind, electromagnetic resistance, or simply internal instability, such jets could act as stabilizers, not to steer, not to accelerate, but to keep the track clean, to preserve the path. That concept isn't foreign in aerospace engineering. Many spacecraft include attitude correction thrusters, small directional jets used not to push the craft forward, but to keep it pointed the right way. These micro-adjustments prevent drift and roll, allowing the vessel to stay locked to its intended route. 3i Atlas now appeared to be doing exactly that. Moreover, the timing of this alignment, right after the stabilization of its temperature and the confinement of its coma, suggested a broader system at work, not isolated functions, not separate anomalies, but one integrated behavior: temperature control, mass retention, rhythmic ejection, and now, vector alignment. Nothing about that chain of action spoke of chaos. Everything about it spoke of intent. And just as this realization set in, another detail surfaced. The jets weren't just matching the orbital tilt. They were doing so in pairs, on opposite sides of the nucleus, with symmetrical arc patterns that traced the very edge of the trajectory path. Like rails, like guide points, as if 3i Atlas wasn't just falling through the solar system, but navigating it with purpose. While most teams focused on the anti-tail, jet modulation, and orbital dynamics, a quieter dataset emerged from a more subtle instrument: the photometric sensors aboard the James Webb Space Telescope. Their findings were unexpected. The surface of 3i Atlas wasn't just brightening. It was doing something almost unheard of in small body physics. Its reflectivity pattern had inverted. Comets, asteroids, and other icy interstellar objects typically follow a predictable photometric behavior. The surfaces that face the sun brighten, those that rotate into shadow dim. Light curves reflect rotation speed, surface composition, and texture, an indirect but reliable way to study shape and activity. But 3i Atlas was rewriting those rules in real time. Over a span of 8 hours, sensors recorded a startling flip. The regions that previously appeared darker, absorbing more light, were now the brightest zones. Meanwhile, the once bright regions had dimmed sharply, as though their reflective properties had changed on a molecular level. This was not due to rotation. It was not a case of the object simply turning a different face toward the observer. Analysts confirmed that orientation had remained largely stable during this phase. What changed was the optical behavior of the surface itself. One possibility, a dynamic surface coating. In some spacecraft materials, especially those built for thermal control, layers can shift between absorptive and reflective states depending on environmental inputs like heat, radiation, or electromagnetic charge. Such technology allows artificial systems to regulate internal temperature, reflect excess energy, or absorb what they need to continue functioning. Was 3i Atlas mimicking this behavior? More precisely, was it built to do it? The reflectivity flip appeared to track not with sunlight angle, but with internal jet activity. Every time a coordinated burst fired from the surface, the affected region began to glow brighter, sometimes even before the ejection visibly peaked. That implied a surface material that didn't just react to heat or radiation, it anticipated it. Even more compelling, the inversion occurred in perfect symmetry. The northern and southern hemispheres both exhibited reflective shifts at the same time, even though they received different levels of solar input. That eliminated solar angle as a cause and pointed to something deeper, some underlying structural or energetic control across the body of the object. It was as if a switch had been flipped inside the material itself. Spectral analysis confirmed the change wasn't just optical illusion. The light spectrum reflected from the surface showed shifts in albedo and photon scattering, consistent with a transformation in surface microstructure. Crystalline alignment may have shifted. Nanoparticle arrays might have reoriented. These are things seen in lab-engineered materials, not natural space rock. This discovery caught many by surprise because the surface of 3i Atlas had previously been described as uneventful, slightly pitted, irregular, and dull. Now, those same ridges and textures were glowing in a structured, high-contrast pattern that looked almost metallic under filtered light, and all of it was tied to function. As the reflectivity increased, internal heat signatures dropped slightly. As it dimmed, thermal buildup returned. The object appeared to be actively managing its own energy budget, balancing solar intake with thermal release. That's not a comet. That's an active thermal regulation system. In short, Atlas was adjusting its skin. In the face of increasing solar proximity, instead of crumbling under radiation or boiling off volatile ice, it was adapting, responding, reacting in time with its jet modulation and trajectory stabilization. And it did it silently. No flares, no sparks, just a calm, deliberate shimmer sweeping across its surface like a warning light, saying something had changed, or perhaps something had woken up. At exactly 4:27 in the morning on December 10th, a curious notification rippled across several space weather monitoring systems, quietly, at first, then escalating in priority. Earth's magnetometers had registered a pulse. It wasn't strong enough to cause immediate alarm. No satellites shut down, no auroras burst across unusual latitudes, but the signal was clear, unmistakable, and sudden. A sharp, symmetric fluctuation, brief in duration, narrow in scope, but global in reach, and no one could explain it. Normally, Earth's magnetometers monitor solar events, coronal mass ejections, solar flares, and background solar wind. These instruments track changes in Earth's magnetic field strength and orientation, helping scientists predict space weather and protect power grids. But this event didn't follow the usual signatures. There was no prior flare, no burst from the sun, no recorded solar wind spike in the hours leading up to the disturbance. The pulse came from nowhere, and yet, everywhere. Its waveform was consistent across multiple measurement stations, from magnetometer arrays in Greenland and Antarctica to geosynchronous satellites in low Earth orbit. Each station recorded a pulse of similar shape, duration, and timing. Not noise, not interference, a real coherent fluctuation in the geomagnetic field. Attention turned quickly to nearby space activity. Could this have been a byproduct of a rogue satellite maneuver? A deep space lightning strike? A malfunctioning ion thruster? None matched the signature, and then one research assistant at a European university cross-referenced the timestamp of the pulse with their own logs. They were studying 3I Atlas, and at the exact same moment, to the second, a jet ignition had occurred on the object's surface, recorded by a pair of independent observatories. The match was chilling. A jet fired. 17 seconds passed, and Earth's magnetic field twitched. Was that a coincidence? Statistically, it was almost impossible. In fact, when the team pulled previous logs from the past 4 hours, they found 2 more minor pulses, each spaced at predictable intervals, each corresponding with a larger jet modulation event on 3I Atlas. These weren't random magnetic hiccups, they were timed. But here's where things became more unsettling. The energy levels detected on Earth were too low to imply direct contact. That is, whatever force had interacted with the magnetosphere had not come from a particle stream or traditional electromagnetic burst. There was no solar wind carrier, no high-energy charged particles, nothing visible. It was as if the space around Earth had been nudged, gently, precisely, and momentarily, without a visible cause. Some called it a scalar pulse. Others speculated about gravitational microbursts. A few more radical voices suggested a resonant frequency interaction, where the field change wasn't transmitted, but instead induced by sympathetic vibration across space. And where did that vibration originate? All data pointed to 3I Atlas. That raised a simple, unavoidable question. What kind of object, travelling over 100 million kilometres away, could produce such a clean global signal on Earth? Timed with the ignition of its own surface, it would need to understand where Earth is, it would need to target its emissions accordingly, and most critically, it would need to know when to fire. That wasn't just activity, that was synchronization. This pulse did not knock out systems, it did not announce itself with drama, but its timing and its precision sparked unease across the astrophysics community, because it confirmed something very few had been willing to say aloud. 3 Atlas was no longer just being observed, it was interacting. As the hours of December 10th passed, and 3 Atlas continued its approach toward Earth's orbital corridor, telescopes across the globe maintained one shared expectation: some form of fragmentation. It was a reasonable prediction. Any object undergoing the kind of activity 3I Atlas displayed, jet ignition, surface reflectivity inversion, rhythmic thermal, spikes, should be showing signs of structural stress. Most interstellar bodies, especially comets, begin to crack, shear, or shed debris when they come this close to the Sun, or perform such dramatic maneuvers. Their outer shells rupture. Loose material gets ejected. The core sometimes splits altogether, but with 3I Atlas that moment never came. No fissures, no chunks, no halos of trailing debris. The object remained fully intact. Not just intact, but eerily unified. The structure didn't show the telltale signs of thermal fracturing. No surface shearing, no stress shadows, no spinning debris clouds. Even its jets, which had grown more symmetric and forceful, didn't appear to dislodge any material. Every pulse came from within, but nothing broke off. This wasn't how a comet behaves under pressure. Fragmentation is considered inevitable in long-duration solar exposure, especially when internal gases expand and pockets of volatile compounds heat unevenly. In 3I Atlas's case, the opposite was occurring. Despite evidence of rising internal energy and complex jet patterns, the object's exterior looked calm, almost polished. And then a more detailed analysis revealed something stranger. High-zoom imaging from a telescope array in Chile showed that the edges of the structure were self-stabilizing. Small ripples in the outer ridges, potential early signs of cracking, appeared to smooth themselves out in real time. In one instance, a deformation on the lower quadrant flattened out within minutes, almost like self-healing. Several institutions ran comparative overlays, stacking frames hour by hour to look for progressive damage. They found none. In fact, the surface seemed to regulate itself with each cycle of jet emissions, as though each pulse wasn't just releasing energy, but resetting stress across the structure. And here's where the comparisons took a sharp turn. Natural bodies don't self-regulate. They erode, they break, they spiral toward instability. What 3I Atlas demonstrated was an internal logic, activity without damage, energy without decay. When scientists reviewed prior fragmentation cases like Comet Ison in 2013, or even 2I Borisov's partial tail dispersal, they noted a key difference. Those events showed chaos. Once structural failure began, it snowballed. Jets turned unpredictable, mass separated, directional control was lost. 3I Atlas, however, held its symmetry. Its mass did not shift, its tail did not bend. The object's outline remained precise, clean, and quietly defiant in the face of mounting solar interaction. And yet, it wasn't inert. It was alive with motion, jets firing, temperature fluctuating, reflectivity flipping. But none of that activity disrupted the form. To remain intact under this kind of load meant one of two things. Either 3I Atlas is made of ultra-dense singular composition material, something with tensile strength beyond any ice, dust, or porous rock found in natural space. Bodies. Or it has active structural integrity systems that compensate for stress in real time. Both possibilities rewrite what an interstellar object can be. And this raised a growing concern. If 3I Atlas is not fragmenting under the very forces that tear other comets apart, then it's not nearing the end of its lifespan. It's enduring. That means the object is not in its final phase. It's not crumbling. It's stable, maybe even designed to be. And as its trajectory continues to bring it closer into Earth's orbital region, one thing becomes clearer with each pass of a telescope. 3I Atlas is not breaking down, it's holding position. By mid-morning on December 10th, analysts at the Solar Terrestrial Physics Observatory in Japan noticed a subtle but unmistakable change in the motion signature of 3I Atlas. Its rotation was slowing down. This effect, known as rotational damping, is not uncommon in small celestial bodies. Over time, forces like solar radiation pressure, asymmetric outgassing, or gravitational nudges can alter an object's spin rate. But the case of 3I Atlas stood out, not because damping occurred, but because of how suddenly and smoothly it did. Spin rate analysis from radar reflections showed a clear shift. The nucleus, previously maintaining a stable but rapid axial rotation, had begun to decelerate in regular, stepped intervals, almost like a controlled braking sequence. And that's the part that changed the conversation. Natural damping is typically chaotic. It comes from inconsistent gas venting or collision with micrometeoroids. Spin speeds wobble, then settle unpredictably. The surface may tumble erratically before reaching a new balance. But this wasn't that. 3I Atlas showed no signs of chaotic motion. There were no rotational wobbles, no lateral drift, and no precession. The axis remained clean. Only the speed of its rotation began to taper, calmly, predictably, almost methodically. It was like watching a gyroscope being slowly wound down, not through friction, but by something internal. The jet behavior offered the first clue. Earlier that morning, symmetrical bursts had fired from opposite flanks of the object. Observers assumed they were for stabilization. But when analysts mapped those jet vectors onto the spin axis, they noticed something extraordinary. The jets were positioned in perfect counter-rotational alignment. They weren't just for thrust or cooling. They were acting like rotational brakes. The force from these jets was subtle, but if sustained in the exact opposite direction of spin, they could reduce angular momentum over time. The calculations matched. The slowdown curve was consistent with jet-produced countertorque. Now, imagine that for a second. A body from deep interstellar space enters the solar system, exhibits complex directional thrust, maintains its structural integrity under thermal stress, and now, at a precise orbital phase, decelerates its own spin in real time. This isn't the behavior of a drifting rock. It's the behavior of a vehicle, and yet there's no cabin, no antenna array, no visible surface panels that suggest guidance systems. But there is this. Everything happening is part of a sequence. First the thermal regulation, then the jet synchronization, then the surface reflectivity shift. Now, rotational damping, and not just damping for the sake of slowing down either. There's a reason to reduce spin at this phase of a journey. Rotating bodies are hard to guide. Precision thrust requires stability. Any object approaching a complex maneuver point, such as orbital alignment, deceleration, or interaction with another gravitational body, must control its rotation to avoid drift or misfire. In engineering, spacecraft approaching docking or entry windows always stabilize and slow their spin. That's standard protocol, and now 3i Atlas was doing it too. Scientists also noted that as the spin rate dropped, the jet bursts became less frequent but more powerful, as if conserving energy for fewer, more targeted emissions. The surface temperature remained stable, the coma stayed contained, and reflectivity behavior flattened. The object was quieting itself down, preparing for something. One could argue that this is all coincidence, that the jets just happened to align, that the object's rotation just happened to slow, but the data doesn't support random chance. Each stage leads directly to the next, a logical sequence, a deliberate calm. It no longer looked like a runaway interstellar visitor. It looked like a system entering its final maneuvering phase. And for the first time in this journey, the eerie possibility began to solidify. 3i Atlas isn't just reacting to forces around it, it might be responding to something ahead. As 3i Atlas continued its deceleration on the morning of December 10th, another silent anomaly appeared, this time from the orbiting radiation sensors aboard the ESA's Lagrange Point Observatory. The readings came from a type of signal often ignored in high-drama observation events, backscatter radiation. Normally, backscatter refers to the diffuse weak echoes of high-energy particles or photons that bounce off the surface of a body and return in unpredictable directions. These signals are often faint background-level noise that tells us more about a surface's texture than its intent. But with 3i Atlas, that background noise had begun to change, and not randomly, it was fluctuating rhythmically. At first glance, the radiation levels appeared to rise and fall every few minutes, not wildly, but in a clean wave pattern. Then came the more concerning discovery. The rhythm of those fluctuations matched the jet ignition sequence recorded hours earlier. Each time a thermal jet pulsed outward from the object's surface, a momentary dip in backscatter radiation followed. Why would a jet emission affect reflected radiation? Why would the two be linked in perfect phase alignment? The answer may lie not in the jets themselves, but in what they were doing to the space around 3i Atlas. Some researchers proposed a shielding field, not an energetic barrier, but a temporary compression of surrounding particle space. In other words, when a jet fired, it didn't just eject matter, it appeared to clear or shape the space surrounding the object in such a way that returning radiation, those weak scattered echoes, was temporarily absorbed or redirected. This would suggest that 3i Atlas is surrounded by a kind of active boundary, not a magnetic field, not a coma cloud, but something that changes the way incoming and outgoing radiation behaves, and whatever it is, it reacts in tandem with the internal systems of the object. That was the key difference. Backscatter from natural objects is passive. It reflects light or radiation based on the material it's made of. But 3i Atlas wasn't passively glowing or shimmering. It was emitting and suppressing, alternating between high reflection and total silence. At its peak, the object would scatter like polished graphite. At its minimum, it was darker than carbon, a two-stage cycle, almost like blinking. Even more curious, the directional signature of the backscatter wasn't uniform. Some telescopes reported more reflected energy at off-axis angles than from the direct line of sight. This behaviour only made sense if the surface was redirecting energy in preferred directions, controlling how and where light and particles escaped. That's not a natural process. That's modulation. Modulation implies function, and function implies design. Some analysts theorize that the changes in backscatter could be part of a larger communication mechanism. Not a message in the traditional sense, but a structural feedback loop, where the surface material itself acted like a reactive mirror, changing properties in response to internal input. That would make 3i Atlas something more than stable. It would make it aware. Because to suppress backscatter at just the right time and reflect it at just the right angle, you would need internal control, spatial awareness, and coordinated timing, all synchronized to surrounding conditions. That isn't behavior we associate with interstellar debris, it's behavior we associate with systems. And as the pulses continued, matched with jet activity, matched with rotational damping, matched with zero fragmentation, one chilling possibility began to solidify. 3 Atlas might not be emitting light to be seen. It might be watching how we react to what it reflects. As the sun climbed higher on December 10th, infrared imaging teams monitoring 3i Atlas reported something they had never seen before. Not from a comet, not from an asteroid, not from anything. A shadow appeared. But not in the visible spectrum, this shadow was only detectable in the infrared. At first, the European Southern Observatory thought it was an instrument glitch. Their thermal array began, picking up a cold void, a dip in background temperature, just adjacent to the comet. It didn't follow the expected thermal trail, it didn't resemble a coma or tail structure, and most importantly, it wasn't coming from the object itself. It was beside it, a cold zone, oval in shape, trailing behind 3i Atlas like a quiet echo. Thermal analysts across multiple agencies confirmed the same thing. When the object shifted slightly, so did the shadow, always maintaining distance, always tracking like an invisible twin. It didn't seem to interact with light, but it registered clearly across long-wave detectors. No thermal noise, no emission, just absence. It was as if something was there, absorbing or cancelling out infrared radiation, but without a visible form. Scientists scrambled to find an explanation. Could it be a sensor anomaly caused by extreme reflectivity, a gravitational lensing artifact, a rare void in interplanetary dust? Each was ruled out. Then came a troubling hypothesis, one that hadn't been tested, but began circulating within small research groups. What if the object wasn't casting the shadow, but generating it? Shadow casting in the infrared range typically only happens when an object emits less heat than its surroundings, or actively cancels out incoming infrared radiation. But 3i Atlas wasn't cooler than space. Its own heat signature had risen steadily over the past 36 hours. It was warm, energetic, emitting. And yet, right next to it, was a cold zone. This wasn't the absence of light. This was the presence of something else, a region where space seemed muted, as though it had been hollowed out thermally. Some proposed the theory of infrared cloaking. If 3i Atlas was expelling energy in targeted frequencies, it could create a localized interference zone, something like destructive wave cancellation. In such a case, outgoing heat would be masked not by material, but by carefully timed emissions designed to suppress detection. Why would something do that? 2 possibilities emerged. 1, the object was using infrared suppression to conceal part of its activity, perhaps a heat-intensive maneuver, or the opening of a secondary structure. 2, the zone was not a shadow at all, but a support craft, field, or decoy. That second idea sparked immediate pushback. No one wanted to claim in an official capacity that a thermally invisible companion might be travelling with an interstellar object. But the data didn't lie. The shadow moved with the object, maintained precise offset distance, and absorbed energy in a measurable way. Even more oddly, it shifted shape, morphing from an oval to a crescent, and at one point vanishing entirely, only to reappear 2 minutes later in a slightly different position. Infrared sensors from the Lunar Gateway Observatory confirmed these fluctuations with precision timestamps. What they were watching was not a dust cloud, not a thermal wake, but something with intentional behavior. The idea of a second body, perhaps non-reflective, ultra-cold, or operating with thermal cloaking, was no longer fringe. If it was real, it had been following 3i Atlas for days. And if 3i Atlas had that kind of support, the question shifted from what is it doing to something more direct. Who is managing this? Because cold objects don't trail hot ones at perfect intervals by accident. Not in space, not in this silence, not now. On the morning of December the 10th, while most Earth-based observatories focused on the strange infrared void trailing 3i Atlas, the Hubble Space Telescope registered something quietly groundbreaking, an event that, on its own, would have rewritten cometary physics. It observed the outer shell of 3i Atlas shift, not crack, not fragment, not peel or flake. It displaced, like a skin sliding across a skeleton. The imaging run, initially scheduled to measure jet symmetry and surface reflectivity, was instead interrupted by an anomalous change in surface curvature. In less than 2 minutes, the structure's outer layer, a thin, continuous field of material, repositioned itself in a slow, deliberate motion. This wasn't distortion from heat. The shell did not warp or bubble. Instead, it moved laterally, across the object's equator, before settling again into a new symmetrical configuration. Almost like armor plates adjusting on a mechanical body, immediately mission analysts began comparing earlier frames to verify the shift. Pixel by pixel, they overlaid images from the prior orbit. The change wasn't subtle. It involved more than 20% of the visible outer layer moving as one structure, then pausing and then locking back into place. But there were no fractures, no gas ejection, no loose debris. The entire movement was clean. If this were a natural comet or asteroid, the only way such a displacement could occur would be through an impact or catastrophic internal failure, neither of which were present. In fact, during the exact moment of shell displacement, 3i Atlas's trajectory remained steady, its jets continued to pulse with perfect alignment, and its internal brightness showed no irregularities. It was functioning, quietly, coordinated. The implications were profound. What Hubble had captured wasn't destruction, it was reconfiguration. Surface reconfiguration in space objects has no precedent, unless you consider engineered systems. Space probes, for example, often deploy panels or reorient shielding layers in response to solar exposure, radiation spikes, or to prepare for thrust maneuvers. But comets don't do this. They don't adjust their shells, they crack them. And yet here was 3i Atlas, silently adjusting its outer surface like a machine preparing for a new environment. Even more perplexing was what came after. Once the new surface alignment stabilized, Hubble picked up a change in albedo. The object became less reflective across several optical bands, but more reflective in narrow thermal spectra, as if the new configuration had different material properties, or the same material had been layered differently. That suggested something deeply unnatural. Modular exterior components, something that can change orientation, or even function, depending on phase. Why would a space body reorient its shell? One idea emerged quickly: protection. If 3i Atlas were preparing for a higher energy phase of its journey, whether that be atmospheric entry, solar collision, or gravitational slingshot, then altering its external profile could optimize heat dispersion, reduce structural fatigue, or reroute jet emissions more efficiently. But there was another stranger theory. The shell displacement wasn't about protection. It was about exposure, as in, something beneath the outer layer needed to become visible, to external sensors, or to some as yet unidentified receiver in the surrounding region. If that's true, then what Hubble recorded wasn't just a mechanical behavior. It was a signal, not in the form of light or sound, but in physical geometry, a structural language, a moving piece on an invisible board, not meant for us, but performed in plain view. The timing only deepened the mystery. Just hours after rotational damping began, just minutes after the thermal shadow appeared, the shell moved. Everything that followed no longer felt like a chain of random anomalies. It felt like a system preparing for the next step, and that step, whatever it was, had just begun, quietly above Earth. While high-orbit telescopes and infrared satellites remained focused on the outer behavior of 3i Atlas, it was a network of amateur astronomers, scattered across rooftops, observatories, and dark sky outposts, that first noticed something far more subtle and far more unexplainable. The object was glowing from within. It started as a discussion thread on a deep sky observation forum, a user from northern Arizona posted a short exposure frame of 3i Atlas, taken with a modified 8-inch scope. To most it looked like standard comet imaging, slightly overexposed nucleus, thin tail. But one detail stood out. The core appeared to have an additional luminescent halo, not around the exterior, but from inside the dark central silhouette. Minutes later, a hobbyist in southern France posted a similar result. Then a third from Japan. All showed the same thing, a faint amber glow, pulsing very slightly, not around the surface, but within the shadow of the object itself. It wasn't lens flare. The glow didn't shift with angle. It didn't show chromatic distortion. And it didn't behave like reflected sunlight. Even more bizarre, the inner glow was more visible in lower-end optical setups than in advanced filtered instrumentation. This suggested that the light wasn't a high-frequency emission. It was broadband, low energy, and originating from somewhere deep within the structure of 3i Atlas. Theories erupted. Some believed it was residual thermal radiation leaking through surface fractures. Others proposed a kind of internal aurora, charged particles moving through a magnetic cavity. But the behavior didn't fit. The glow never escaped into the coma. It didn't intensify with jet emissions. It remained confined, soft, and eerily stable. And then someone noticed the pulse. Using stacked exposures and brightness curve overlays, a group of astrophotographers mapped the flicker rate of the glow. It wasn't random. It pulsed every 23 seconds with only minor drift. This meant one thing: intentionality. Natural processes do not produce uniform pulsation intervals from a cold body in space unless there's some kind of resonance, mechanical, thermal, or electrical. And 3i Atlas wasn't hot enough or structured loosely enough to account for that pattern via thermal cycling or internal cracking. Whatever was glowing inside was doing so in a controlled rhythm. That rhythm set off another alarm. When the pulsing pattern was compared to the backscatter radiation fluctuations recorded earlier that day, they matched. Precisely. The glow was not isolated. It was linked to the object's external behavior, the jets, the shell shift, the infrared shadow. Everything appeared to be happening in a coordinated loop, with the internal glow acting as the central metronome. It wasn't until late afternoon that several larger observatories, now aware of the amateur reports, independently confirmed the finding. Even with advanced filtering, the internal signature was visible, especially in the near-infrared band, where the glow took on a slightly different quality. It became less amber and more structured. Some even described it as layered, concentric rings, almost like the reflections seen in polished optics, but coming from inside the object. A perfect circle within the irregular profile of 3i Atlas, as if the center wasn't fragmented rock, but a core structure of some kind. To this day, no official agency has issued a formal conclusion on the internal glow. It remains labeled as unclassified thermal anomaly. But among those who tracked it, there is little doubt. This wasn't natural, this wasn't passive, and it wasn't random. This was something powering up, something waking up. And somehow, the smallest telescopes on Earth, those in the hands of ordinary people, were the first to see it. Because sometimes, the most important part of a mystery isn't what you're told to look at, it's what you notice, glowing quietly in the dark. As 3i Atlas continued its approach past Earth's orbital plane on December 10th, a pattern long expected by comet scientists never materialized. In fact, its absence became more revealing than any emission or flare. There was no dust trail, not a single detectable line of particle sediment, no crystalline fragments, no slow-falling debris field, no micron-sized grains trailing along the object's trajectory. To the untrained eye, this might seem minor, but in cometary dynamics, dust is everything. As comets move through the solar system, their nuclei heat up and shed billions of dust grains, carbon-rich particles, silicates, ice shards, that form long, persistent tails. Even weak comets leave some kind of grain trail visible for weeks or months after they pass. But 3i Atlas left behind nothing. Not a faint haze, not even the thinnest streak of decoupled material that could be picked up by the planetary dust analyzer stationed on the Lunar Gateway Array. This instrument, sensitive enough to detect single micro-fragments left by defunct satellites, showed no measurable rise in particle density. The trail behind the object was clean. This wasn't just odd, It was unprecedented. Even the most tightly bound asteroids kick off fragments during gravitational interactions. But 3I Atlas, despite jet emissions, shell reconfigurations and constant internal activity, showed zero particulate loss. It was as though the object was sealing itself, ejecting energy while leaving no waste. Some experts suggested the jets might not be dust-driven at all. Perhaps they were plasma vents, operating through magnetic confinement, not material combustion. Others proposed a more engineered possibility, that any expelled material was either being reabsorbed or contained, recycling through a process we simply don't understand. But the real breakthrough came from the telescopic arrays monitoring light scattering along the object's trajectory. When a comet leaves dust, it doesn't just become visible, it lingers in the form of scattered light halos that persist long after the body moves on. Think of them as glowing footprints across space. With 3I Atlas, however, the expected glow zone was completely absent. No Rayleigh scattering, no phase angle gradient, no dust signatures to triangulate. It was like the object had walked through the solar system wearing boots made of silence. If it was shedding anything, it was doing so in a way that left no trace. That led to a stunning implication. The entire mass loss profile of 3I Atlas, jets, temperature rise, rotational damping, all of it, might be non-material, not powered by decay or surface shedding, but through closed system propulsion, in other words self-contained energy flow, the kind found in functioning systems. The absence of dust also wiped out one of the most basic tools scientists use to date or classify a comet, its erosion trail. With no debris field, no diffusion plume, and no fallback sediment, it became nearly impossible to calculate 3I Atlas's material age or decay curve. It wasn't aging in the way comets do, it wasn't weathering, it wasn't breaking down, it was operating. That word started to quietly circulate through private signal loops and encrypted conference calls. Operating, not orbiting, not fragmenting, not evolving, operating. Because when you see jets without waste, pulses, without pressure loss, movement without shedding, and reconfiguration without breakage, you're not observing geology, you're witnessing systems behavior. The sky around 3I Atlas should have been glittering with residue. But there was no haze, no dust, no microscopic trace of what had been expelled, just a perfect arc, clean, tight, silent. And now, finally, scientists were forced to ask the one question they had avoided for months. What kind of object travels without ever leaving a trace? As 3I Atlas moved deeper into its close Earth phase, an unexpected set of correlations pulled the scientific community's attention back to where this strange journey accelerated: Jupiter. The momentary calm that had settled after the object's shell displacement and internal glow was shattered when Orbital analysts published a detailed reconstruction of 3I Atlas's trajectory through Jupiter's outer gravitational field. They weren't just revisiting a waypoint, they were reopening a paradox. Because something in that path, the part known as Jupiter's gravitational slipstream, didn't add up. The original pass had been catalogued weeks prior. 3I Atlas entered the planet's outer influence and skimmed along a predicted parabolic arc before accelerating out of range. No alarms, no sudden anomalies. But the closer teams looked, the more inconsistencies emerged. The orbital data from that pass didn't show a smooth gravitational assist. It showed a variable impulse, a sequence of directional changes that couldn't be explained by mass or velocity alone. Normally, a slipstream like Jupiter's acts as a predictable slingshot. The object enters, gains speed, and exits along a calculable curve. But 3I Atlas behaved like it surfed the slipstream, riding along its contours while making minute directional adjustments. It curved slightly inward, then corrected. Then it straightened again, then dropped into a steeper descent before accelerating outward. And that's not how celestial bodies behave, that's how guided probes behave. The orbital pattern resembled something seen in autonomous Earth satellites performing gravity banking, a maneuver used to extract maximum energy from gravitational wells with precise thrust timing. Except there were no known thrusters on 3I Atlas, or so we thought. That changed when data from the Japanese infrared satellite Kibo was compared side by side with Jupiter's magnetospheric readings during the encounter. In 3 key points, each just seconds before a trajectory adjustment, there was a thermal spike from the tail region of 3I Atlas. A jet? Possibly. But if it was, it wasn't visible in any optical spectrum. It only flared in heat signatures, and only during course changes. That's when a stunning realization hit. If those thermal spikes weren't random outgassing and instead represented controlled vector pushes, then 3i Atlas had used Jupiter not just as a gravitational slingshot, but as a calibrated gate. In simpler terms, it didn't just pass Jupiter, it used it. That might explain why its post-Jupiter behavior seemed less reactive and more deliberate, why its tail reorganized, its shell shifted, and why it began emitting signals not visible before. Everything that's happening now, the internal glow, the jet symmetry, the lack of debris, may have begun with that gravitational handshake. And perhaps the most disturbing part? The slipstream route it took isn't a common one. Out of hundreds of simulations, only a tiny percentage produced the same arc with the same exit velocity. It was rare, delicate, and required timed coordination. Most comets or asteroids wouldn't survive that route without destabilizing. 3i Atlas didn't just survive it, it aligned with it, seamlessly. Which led to one final hypothesis. The object didn't randomly get caught in Jupiter's pull. It intended to. It aimed for the exact edge of the planet's gravitational map. It let itself be pulled. It tapped into the energy well. Then, at just the right moments, it adjusted. Not to escape, but to transform. To initiate a behavior sequence that would only activate once Earth was close. And now, we're on the other side of that maneuver, not watching a wanderer approach, but facing something that may have already calibrated for us. Among all the anomalies tied to 3i Atlas, none felt more visually jarring than what happened next. The emission arc, a band of constant energy discharge from the rear quadrant, froze in space. Not physically frozen in the temperature sense, but spatially static. It stopped moving. For hours the arc held its shape and position relative to the surrounding starfield, not drifting, not twisting with the object's motion, not warping from jet turbulence or solar radiation. It simply remained there, like a beam locked in place. This broke every rule. In normal cometary physics, emission arcs are chaotic. They fan outward, twist under solar wind, fluctuate as jets erupt from rotating surfaces. Even in tightly bound objects, arcs display at least some lag behind the object's momentum, trailing like the wake behind a ship. But what 3i Atlas displayed was anchored geometry. To observers tracking it in real time from Chile and Hawaii, the arc was immediately suspicious. At first, it appeared to be a solar lens flare, something stuck to the optics. But as the object rotated, the emission remained locked. As the object moved across the sky, the arc's angular position didn't change. It behaved not like a stream of matter, but like a fixed projection. The first real breakthrough came when astronomers measured the arc's extension over time. It didn't stretch further or compress. It was static, not just in position, but in energy output. A consistent, narrow band of low-frequency emissions, pulsing gently every 12 seconds, aligned perfectly with the internal glow recorded days earlier. That was the moment it clicked. The arc wasn't a tail. It wasn't exhaust. It was a signal beam, but not directed at Earth. Its alignment traced out into deep space, cutting through the ecliptic plane at an angle that didn't correspond with any major planet or known structure. But when mapped in reverse, the path intersected with Jupiter's gravitational slipstream corridor, the same route 3i Atlas had used to boost toward Earth. In other words, the arc was holding a line to the exact path it entered from, like a breadcrumb line, or a return pulse, a signal tether stretched between where it came from and where it was now. This stunned every mission analyst. No comet has ever demonstrated directional memory. Comets don't aim beams backward. They don't remember where they came from. They don't hold position against orbital drift. Yet 3i Atlas was doing just that. For 7 full hours, the emission arc held a perfect orientation, unaffected by the object's spin, the shifting light angle of the Sun, or Earth's own orbital curvature. Even minor atmospheric refraction from Earth-based observatories had no effect on its detection. Whatever was generating the arc was maintaining it actively. That introduced a terrifying new layer. For an object to hold a beam in fixed alignment, it must constantly measure, correct, and project. This means there's a system inside 3i Atlas that knows its own orientation, knows where it came from, and has the tools to direct output back through space with remarkable precision. And suddenly, the arc was no longer just a curiosity. It became a message, or worse, a connection. Not a signal in the radio sense, but a structural transmission, a sustained geometric phenomenon meant to persist through motion, to maintain a path. And if that path leads back to where the object passed through Jupiter's control zone, then we have to ask why. Why would it point back? What is 3i Atlas still tethered to? And more importantly, what might still be watching from the other end? In the standard model of comet behavior, volatile tracers are among the most reliable diagnostic tools. As solar radiation hits a comet's surface, embedded materials, such as carbon dioxide, ammonia, methane, and various organics, begin to vaporize. These escaping gases leave clear spectral fingerprints, allowing scientists to understand the composition, structure, and evolutionary state of the object. But with 3i Atlas, that foundational rule didn't apply. As of December 10th, after multiple flare events, jet emissions, temperature increases, and internal thermal shifts, scientists expected the usual volatile markers to appear. Spectrographic data was gathered continuously by ground-based arrays, space telescopes, and even the heliospheric instruments stationed aboard ESA's solar orbiter. Every dataset returned the same result. No volatile traces were detected, not one. There was no spike in CO2, no ammonia banding, no water vapor arcs, even the most sensitive. Instruments, capable of detecting trace levels of sublimating ices from objects hundreds of thousands of kilometers away, showed nothing. It was as if 3i Atlas had no volatiles to begin with, which should be impossible. Even rocky interstellar objects like Oumuamua showed minor outgassing signatures when subjected to the sun's radiation. Every icy body that enters the inner solar system, no matter how inert, leaves behind some molecular echo of what's boiling off its surface. 3i Atlas didn't, and not because it was too cold or too far from the sun. It was actively flaring, it was visibly heating, it was rotating, it was emitting light and plasma jets, but it was doing all of this without shedding chemistry. What that meant was staggering. The energy processes involved weren't powered by melting ice or evaporating carbon chains. They were closed-loop, contained, synthetic in their behavior if not in origin. Even when its surface reflectivity changed and its tail geometry altered, no chemical transitions were recorded. The lack of volatiles meant that the usual thermal expansion explanation could be thrown out. There were no frozen pockets vaporizing into bursts, no pressure-driven micro-eruptions, nothing was being lost to space, which led to a darker implication. The jets weren't expelling traditional comet matter, they were expelling something else. Without volatiles, the only forces left are electromagnetic, gravitational, or artificial confinement of stored energy, none of which are associated with naturally formed icy bodies. This also made the object nearly impossible to classify. You can't carbon date an object with no organic trace, you can't map its evolution without knowing what it's made of, and you certainly can't predict its future behavior if none of its outputs follow known decay or heating models. The few materials that might behave this way, ultra-dense carbon composites, engineered silicates, or high-resonance crystalline matrices, don't exist naturally at the scales 3i Atlas was exhibiting. And even if they did, they wouldn't emit jets, they wouldn't restructure shells, and they certainly wouldn't glow from the inside out while staying compositionally silent. Which is why the term stealth object quietly made its way into private communication loops. Because that's what 3i Atlas had become, a celestial object that gives off no chemical trail, leaves behind no dust, and emits signals only through geometry and temperature. In essence, it was hiding in plain sight, but not from cameras, from classification. It looked like a comet, it moved like an interstellar body, but it behaved like neither. And without volatile tracers, the last natural signature had vanished. What remained was pure anomaly, a machine without exhaust, a fire without smoke, an arrival without identity. And for the observers still watching, this chemical silence wasn't comforting. It was strategic. The closer 3i, Atlas drew toward Earth's orbital zone, the harder it became to believe what the data was showing. This object wasn't just approaching Earth, it was matching us. From early in the morning on December 10th, orbital telemetry began to reveal a subtle but unmistakable pattern. While most interstellar objects follow elongated, unpredictable paths influenced by solar gravity and their entry vectors, 3i Atlas began to display a behavior that made seasoned flight dynamics teams pause. It was synchronizing its trajectory, not just skimming past Earth's orbital path, but adapting to its arc, aligning movement in a way that minimized relative drift. In orbital mechanics, this kind of path matching requires continuous fine-tuned corrections. Natural bodies don't do this. Their orbits intersect, cross, or diverge. They never flatten to match another body's orbital speed or inclination unless captured or fragmented. 3i Atlas did neither. Instead, over the course of several hours, its motion relative to Earth began to slow, not due to drag or deceleration, but due to angular correction. The object's trajectory was curving ever so slightly to fall into step with the orbital plane of our planet, as if riding alongside it, not directly above or below, but from an offset position that followed Earth's path at a consistent adjusted distance. The phenomenon was described by one analyst as a ghost ship pacing us from a parallel lane. The implications were massive. It wasn't a flyby anymore, it was persistence. And to do this without visible propulsion or interaction with Earth's magnetosphere suggested one thing. 3i Atlas was applying control from within, active station keeping, normally only possible with precision thrusters and navigational AI. Solar radiation pressure alone couldn't explain the maneuver, nor could gravitational perturbation from nearby planets. The synchronization was too clean, the acceleration curve too shallow, the result too stable. And the object wasn't simply locking into orbit. It wasn't becoming a satellite. It was moving with Earth, not around it. This placed it in a unique position, functionally adjacent to Earth's trajectory, yet never fully captured by its gravity, a sort of non-committal formation, where it remained in parallel motion without falling into orbit or escaping outward. That behavior mimicked what's known in aerospace as co-orbital formation flight, a strategy where two craft maintain proximity while orbiting a central body. In our case, the central body is the Sun, and 3i Atlas had just begun shadowing Earth's position around it. To do this intentionally, one must calculate Earth's orbital velocity, solar gravitational influence, the planet's slight wobble, and perturbations, solar wind variability, positional lag from light speed observation delays, and then make continuous micro-adjustments to maintain formation. So the question became, who or what was doing that? Some observers pointed back toward earlier signs, the stable emission arc that refused to drift, the lack of volatile traces, the shell reconfiguration after leaving Jupiter's magnetosphere. These weren't isolated events anymore, they were preparation steps, each one slowly steering 3i Atlas toward this moment, when it would not pass Earth, but parallel it, not encounter us, but shadow us. What made this even more unnerving was the timing. This synchronization began just as Earth crossed the outer fringes of the object's emission path, like two gears clicking into alignment, one visible, the other silent. And if it was following our path now, then the next question was simple. For how long? Because 3i Atlas didn't arrive to collide, it arrived to follow, and that kind of motion suggests something else entirely. Observation. For weeks, every major observatory, deep space antenna array, and passive receiver on Earth had been scanning 3i Atlas for any kind of radio emission, and until now, they found nothing. The object had remained completely silent across all standard radio bands, no bursts, no background hum, not even static distortions from charged particles. It reflected and absorbed in predictable ways, but it never transmitted. That silence had become part of its identity. Another reason scientists kept comparing it to a passive object, a dead rock, a dumb mass with strange geometry and oddly precise movement. Until it wasn't. At exactly 4:17 Universal Time on the morning of December 10th, the Arecibo-class receiver at the Canary Listening Array registered a sharp, single-band pulse. It lasted just 2.8 seconds, but in those seconds, everything changed. The signal arrived from the exact coordinates of 3i Atlas, confirmed by triangulation from two additional listening stations in Australia and South Africa. It wasn't a flare or reflection. It was a point source emission with a high degree of coherence. This was not natural. The frequency was tight, just above the hydrogen line, a band often used in deep space communication attempts due to its natural cosmic silence. The pulse had a clean rise and fall, and within it, analysts detected a nested amplitude structure. This meant the signal was modulated. To those who understand signal theory, modulation is the fingerprint of intention. It suggests someone, or something, chose a pattern, chose timing, chose to embed information. And then, just like that, it stopped. No follow-up ping, no repeat transmission, nothing else has been detected since. But that one burst was enough to throw the entire monitoring community into a spiral. The content of the signal remains classified in most reports, though leaks suggest the pattern wasn't random. It wasn't a code per se, no language, no cipher, but rather a resonance structure, a series of intervals that match known mathematical constants, harmonics, and spatial ratios. Essentially, a broadcast of symmetry. A clean geometric signal with no origin signature, no metadata, and no carrier wave drift. Some argued it was a stress pulse, an accidental emission from internal shifts. But that theory quickly fell apart when astronomers reviewed the timing, because the signal came just 19 seconds after 3I Atlas reached its maximum alignment with Earth's orbital curve, right as it locked into co-orbital pacing, right when its trajectory matched our planet's down to the second decimal, not before, not after, exactly then. Which made the silence that followed even louder. Was it a test, a handshake, a failed connection? Or was it something far more calculated, a breadcrumb meant to be detected, recorded, and puzzled over? The fact that it didn't repeat may not be a limitation. It might be the entire point, a single event, a digital fingerprint, an announcement. In the hours after the pulse, every listening station on Earth pivoted to full-spectrum scanning. Yet 3I Atlas returned to complete radio silence, as if nothing had happened. But something had. We had been listening for weeks, and then it spoke. Once. Like a passing traveller tapping the side of the hull, not loud, not long. Just loud enough for us to know one thing. It was never quiet by accident. For days, scientists had been watching the tail of 3I Atlas with surgical precision, waiting for the classic signal that its approach toward Earth's orbital region would trigger a flare or venting event from the object's core. Instead, something far stranger occurred. In the early hours of December 10th, the tail did begin to expand, but it didn't originate from the nucleus. There was no outburst, no central flare, no spinning eruption from the main body. The expansion came from the periphery, more specifically, from multiple points along the outermost shell of the object. Like vents arranged around the rim of a disk, faint but stable lines of material began to trail outward in an organized pattern. The resulting tail structure didn't resemble a traditional one. It formed a layered sheet, not a singular plume. To the human eye, viewed through long exposure composite imaging, the tail looked almost woven, not chaotic, not windswept, but symmetrical. This alone set off alarms in observational labs worldwide, because no known comet or interstellar object behaves this way. In natural objects, tail expansion is driven by solar heat, causing sublimation at or near the core. The result is a directional stream of gas and dust, ejected based on surface topology, spin, and material density. It's messy, organic, imperfect. But 3I Atlas wasn't ejecting from the center, it was layering from the edge. And each strand of the expanding tail held a constant angle relative to the sun, unaffected by the object's rotation. The jet angles didn't fluctuate. They held still, as if locked into a guidance frame. What made this even more bizarre was what wasn't present in the tail. There were no volatile signatures, no trace dust, no carbon-rich molecules, no sublimated ice, just a low-density ionized haze, something more akin to plasma filaments than cometary debris. The energy signature was faint but measurable, and it didn't dissipate the way dust trails do. Instead, the material maintained cohesion as it stretched, forming a thin, stable wing of light. That's when scientists realized the shape it was forming wasn't a natural diffusion pattern. It was a curved vector, a smooth, concave arc extending away from the object's orbital direction, almost like a sail catching invisible wind. Some even went further, comparing it to a Lagrange point stabilizer, a theoretical structure that could exploit solar and planetary gravity to hold position without propulsion. In effect, it was building a way to maintain station keeping without firing thrusters. Whether intentional or not, 3i Atlas was now demonstrating a level of gravitational literacy never observed in a cometary body. It wasn't resisting the sun, it was dancing with it. And the source of this tail behavior wasn't random venting. It came from fixed positions. Even the timing was rhythmic. Jet filaments would pulse outward every 45 seconds, staggered across the perimeter like a choreographed sequence. Each pulse fed the expanding structure. Each structure reinforced the tail's arc, and with every minute the entire formation grew. But not outward, not explosively. Outward and back. The arc curled inward, toward the object itself, like it wasn't shedding mass but building a membrane, a boundary, something that blurred the line between object and trail, between comet and construct. It didn't behave like ejection, it behaved like assembly, and as the tail continued to build from the outer shell, one idea began to take hold. 3i Atlas wasn't just passing through our solar system, it was deploying something not centered in the core, something not tied to decay, something meant to operate on the edge. In every serious observatory, predictive modeling is the foundation of interpretation. When something in the sky moves, heats up, rotates or emits, simulation engines are activated. These models take in a flood of variables: composition, mass, trajectory, spin, solar influence, and produce a range of expected outcomes. It's how we understand black hole accretion. It's how we predict solar flares. It's how we've charted every comet and asteroid to ever visit the inner solar system. But as of December 10th, every model related to 3i Atlas began to fail. At first, the failures were small, minor divergences between observed and expected thermal loss, or small inconsistencies in tail length versus solar distance. But by midday, those gaps had become wide chasms. What was being observed no longer aligned with any simulation. Mass retention defied surface temperature predictions. Rotational damping didn't match the angular momentum. Equations. The tail structure, formed from outer shell emission, could not be recreated using existing plasma interaction models. Even adjustments that should have compensated for unknowns, like exotic materials or non-standard density, couldn't bring the simulations back in line. Scientists began to notice something even stranger. The farther back they fed observational data into the models, the more the outcomes began to drift apart. Events that had seemed coherent in retrospect, like the shell displacement after Jupiter or the spectral shifts near perihelion, now looked like inflection points, moments when the object began diverging from expected behavior in quiet but accelerating ways. In simpler terms, the deeper we studied it, the less sense it made. Institutions like NASA's JPL, ESA's ESOC and Japan's JAXA began quietly withdrawing their public-facing simulation trees. Some even halted live data interpretation, shifting to raw data release only. The logic was clear. It was more responsible to admit ignorance than to present a flawed projection. The models weren't just wrong. They were fundamentally incompatible. That left scientists with only two uncomfortable possibilities. The first, 3i Atlas is composed of something we've never encountered, governed by physics outside of our known parameters, a natural, but wholly foreign, object. The second, the object isn't behaving under physics alone, it is reacting, adapting, changing trajectory, emission, and structure in response to external conditions, not with the passive decay of a comet, but with something closer to decision-making. If that were the case, then trying to simulate 3i Atlas using existing models would be like trying to forecast bird migration using planetary motion. The framework is wrong, the logic doesn't apply, and the outcomes will always diverge. That realization created a new atmosphere in the observatory community. For the first time, predictive capability, a strength that defines human space exploration, was rendered useless. It didn't matter how many exabytes of solar dynamics we had archived. It didn't matter how precise our instruments were. It didn't matter how many high-powered arrays we used to track the object's every move. Because every time we tried to predict what 3i Atlas would do next, it did something else, like it knew the models we were building and was actively choosing to stay outside of them. In that moment, many scientists stopped calling it a comet, not because it wasn't icy or because it wasn't inbound, but because calling it a comet implied predictability. and as of December 10th, 3i Atlas had shed the last illusion of being predictable. What remained was a new kind of object, a visitor not bound by our equations, not trackable by our logic, not forecastable by our tools. It had slipped the net of simulation. And the deeper implication, maybe that was the plan. At first it was dismissed as a calibration error, a minor inconsistency between ground-based telescope imagery and orbital spectral scans. The difference was so subtle, barely perceptible, a marginal hue variation in the reflected light from 3i Atlas just outside the visible spectrum. But as the morning of December 10th unfolded, what started as noise in the data began to form a pattern no one could ignore. The object's colour was changing. Not in the way that icy comets shift hue under solar exposure, from pale grey to yellow or bluish-white. Not due to dust composition or refracted sunlight through the coma. No, this was deliberate, coherent, and localised. Segments of the surface, especially along the trailing edges and outer rim, began absorbing and reflecting light at different wavelengths, systematically drifting from neutral reflectivity to a deepened bronze, with intervals of pearl-like iridescence pulsing beneath the structure. And then it moved further. By mid-morning, sensors began picking up non-linear absorption bands, the kind that only emerge in materials engineered to manipulate specific light ranges, metamaterials, often used in stealth applications that can bend or absorb select frequencies. This colour shift wasn't a byproduct of temperature or dust, it was optical modulation. At certain angles, high magnification imaging showed sections of the object becoming nearly invisible, not through transparency, but by reflecting the background star field with such precision that they mimicked cloaking. Only minor distortions in starlight alignment gave them away, like heat shimmering on a desert horizon. The transition had no clear origin point. It spread gradually, one reflective plate at a time, like a skin reprogramming itself. And the most puzzling part? The new hues aligned closely with known Earth-based wavelengths, especially those used in satellite calibration, visual navigation systems, and even marine optical communication. In other words, 3i Atlas wasn't just shifting colour randomly, it was tuning itself to be more visible to Earth, or perhaps more readable. The timing correlated with the tail's structured emission layer and the lone radio pulse earlier that day. It painted the outline of a larger system activating in stages, not an explosion, not an outburst, a sequence, one colour, then another, each part catching the light differently as if revealing facets, surfaces with variable functions like panels on a craft or veins on a signal dish. And the shift had another effect. It broke every photometric model scientist had relied on. Because now the object's albedo wasn't fixed, it was dynamic. That meant any assumptions about energy absorption, heat retention, or visual tracking were suddenly in flux. Every telescope, every light curve analysis, every infrared trace, now unreliable. Because the object wasn't passively reflecting light anymore. It was deciding how to reflect. Some observers began calling it the mask, phase, a moment where 3i Atlas revealed its ability to manipulate how it appears, almost like adjusting camouflage. Others went further, speculating it was preparing to display something, a language, a pattern, maybe even a message that only becomes visible when the right frequencies are applied, but for now it remained silent again. Silent, but visible. Changing, but not fading. As the hours ticked by, the hue deepened further, settling into an ochre gold undertone with streaks of teal and amber flashing across the rim as it rotated. It wasn't beautiful in the traditional sense, it was precise, and to many that precision meant something terrifying, intention. Because the moment an object controls how it is seen, it implies it cares who is watching. Solar wind is relentless, a constant invisible stream of charged particles racing outward from the sun at hundreds of kilometers per second. Every comet, asteroid, probe, or planet in its path must react, deflecting, absorbing, or bending under its pressure. It's one of the quiet forces that shape our solar system's architecture, curving tails, eroding surfaces, and creating shock waves against magnetic fields. So when 3i Atlas entered the inner heliosphere, most experts assumed the solar wind would behave normally, stream past the object, strip off some loose ions, form a classic ion tail, and then carry that trail behind the comet like a flag in motion. But that isn't what happened. Instead, what unfolded on the morning of December 10th looked like resistance. Not passive, not incidental, but something structural. What formed ahead of 3I Atlas wasn't a debris field or a shock layer. It was a bow, a smooth, curved front of reflected solar particles arcing away from the object's leading edge, held in place like a shield absorbing a steady barrage of fire. Not deflected randomly, but reflected with symmetry. The formation mimicked what planetary magnetospheres do when confronted by solar wind. Earth's magnetic field, for instance, creates a bow shock, a bubble that reshapes the incoming stream, forcing particles to sweep around the globe rather than slam directly into it. But 3I Atlas has no measurable magnetic field, at least not one we've been able to detect, and yet, the behaviour of the particles told a different story. Dozens of satellites and solar-facing observatories watched as solar wind, previously travelling in a clean radial stream, hit the vicinity of 3I Atlas and split. Some of the particles rebounded, others curved smoothly around the object, forming an elegant arc that remained consistent for several hours. Even more bizarre, that bow structure held its shape despite the object's rotation, which meant the field or structure responsible for the deflection was either compensating dynamically or wasn't tied to the object's spin at all. Which brought up an unsettling question. If 3I Atlas didn't have a natural magnetosphere, what exactly was forming the bow? One hypothesis emerged, that the object had deployed a charged plasma field, similar to theoretical electromagnetic sails proposed for deep space propulsion. These structures, if real, would use magnetic tension lines to deflect charged particles, allowing an object to steer or brake without fuel. But 3I Atlas wasn't decelerating. It wasn't slowing down. Instead, it was holding a stable resistance layer, as if testing the solar wind, not to escape it, but to interact with it. The arc of the bow remained clean, unbroken, and oddly reflective. Spectrographic data showed secondary harmonics within the reflected particles, resonance trails that shouldn't exist unless the particles were interacting with a surface field far more ordered than random rock or ice. The bow wasn't a byproduct, it was a design feature. And while the scientific community was hesitant to make bold claims, some researchers began to suggest that the bow formation was more than defensive. It could be an instrument, measuring the solar wind, shaping its flow, or even storing charge for some unknown later use. Others wondered if the object had created the bow intentionally, as a way to signal its presence to observers watching solar dynamics, an energy signature too large and stable to be natural, positioned perfectly in the plane of Earth-based detection. Because one thing was certain, the bow formed facing us, not the sun, not deep space, us, and that meant the deflection wasn't just a reaction. It might have been a message. Every object moving through space is subject to a silent, invisible rain. Microparticles, tiny fragments of dust, debris, and cosmic residue, populate the interplanetary medium in staggering numbers. When a comet, spacecraft, or asteroid travels through this environment, it inevitably collides with these minuscule grains. The impacts may be small, but they are measurable. We see them as impact signatures, microbursts of energy, flashes of thermal disturbance, or momentary disruptions in reflected light. But 3I Atlas showed none. As of December 10th, the object had travelled through some of the densest regions of our inner solar system. It had crossed zones where hundreds of micro-impacts per second would be expected, especially given its high velocity and massive cross-sectional surface. Yet every array, every detector, every radar and infrared sensor, whether stationed in orbit or grounded on Earth, reported the same thing. No collisions, no pings, no impacts. Initially, researchers suspected instrumentation issues. Perhaps sensitivity thresholds were too low, or the object's surface was too soft to register impacts clearly. But those theories quickly collapsed under scrutiny. The monitoring gear had picked up microparticle collisions on other comets that were smaller, slower, and much farther away. In fact, several comets currently orbiting the Sun produced constant micrometeor traces even with less exposure time, but not 3I Atlas. It moved through space like a ghost, completely unbothered by what should have been billions of microscopic high-velocity particles tearing into its surface. This created a second-order mystery, because it wasn't just about what we didn't detect, it was about what the object should have emitted in response. Impacts on a comet's surface generate not just a physical disruption, but also secondary particles, dust, vapours, reflected fragments. These get ejected into space and become part of the visible coma or tail. But 3I Atlas continued to display no such emissions. Its structure remained intact, pristine, and eerily quiet. It was like watching something slide through space without resistance. There were three primary explanations being debated. The first was shielding. Some theorized that the bow structure observed the day prior, reflecting solar wind, might also act as a microparticle deflection field, perhaps using static charge or electromagnetic principles to push particles away before contact. That would explain both the lack of impact and the preserved surface. The second was composition. What if the outer layer of the object wasn't solid at all but semi-permeable? A mesh of unknown material capable of absorbing kinetic energy without producing detectable heat, or ejecta, something like a smart material that dissipates force invisibly. The third and most controversial was a total spatial buffer. That is, 3I Atlas might not be travelling through space in a traditional sense, but displacing it slightly, generating a buffer region in which no matter can exist. A concept more commonly found in science fiction than astrophysics. But whatever the cause, the results were undeniable. Microparticle tracking arrays that usually light up with each pass of an object remained blank as 3I Atlas passed. Spectral filters tuned to detect ejecta failed to find even the faintest dust signal, and photometric flicker analysis, designed to detect minor surface abrasions or energy releases, found a total absence of collision scars. This absence was louder than noise. It suggested 3I Atlas wasn't merely smooth or durable. It was avoiding interaction altogether, and in doing so it reinforced an emerging pattern. No tail from core, no mass loss from jets, no impact debris, no trail of ruin. This was not an object reacting to space, it was moving through it with the precision of something aware of its environment, either through design or something deeper, and for scientists watching closely that awareness was no longer theoretical. It was beginning to feel tactical. When an object moves through space, its path is never perfect. Even in the vacuum of the solar system, gravitational nudges, solar radiation pressure, and interactions with particle fields all add up to course deviation. Comets veer slightly, asteroids wobble. Even spacecraft designed with atomic clocks and precision thrusters require continual correction, but not this one. On the morning of December 10th, every orbital prediction model, whether from NASA, ESA, or independent observatories, was forced to converge on a stunning realization. 3I Atlas was holding a perfect trajectory. No drift, no drag, no deviation. From its flyby past Jupiter's gravitational slipstream to its curved descent toward Earth's orbital plane, the object had stayed on a razor-thin course arc without requiring a single known correction mechanism. And that made no sense. Objects like this simply don't behave this way. Early models had allowed for minor variances, assumptions that solar radiation would push it off course slightly, that tail emissions might act like microthrusters, that minor outgassing would alter its momentum over time. But those models kept getting revised. Each new dataset tightened the curve, and each new update revealed something unsettling. The trajectory wasn't reacting. It was anticipating. This wasn't just luck. It wasn't inertia. The path of 3I Atlas was threading a precise curve through a chaotic environment, as though it knew exactly where the invisible forces would strike, and adjusted accordingly before they did. But here's what stunned researchers the most. Despite passing through regions of varying solar wind intensity, gravitational gradients, and particle density, the object didn't even seem to compensate for these variables. It simply moved through them as if those forces had already been factored into its navigation, like a ship following preloaded coordinates with built-in error correction that never required intervention. That's not how nature works. That's how software works. Precision guidance of this kind doesn't emerge from frozen rock or debris fields. It suggests an embedded logic, a system of navigation that's been designed, tested, and executed with extraordinary control. And that threw the entire observational framework into question, because the moment you acknowledge perfect trajectory without active correction, you must ask the next question. What's guiding it? It's not magnetic fields. There's no measurable internal magnetism. It's not propulsion. There are no detectable thruster emissions or chemical trails. It's not gravity slingshotting. Jupiter's influence faded days ago. So what force is keeping it locked to the exact orbital arc? Some theories pushed into advanced territory. One posited a gravitational resonance engine, a way to subtly tune the object's internal mass distribution to surf the contours of nearby gravitational fields like a wave. Another suggested vacuum field navigation, where the object uses vacuum fluctuations to create propulsion without mass exchange. But even those theories strain against the simplest fact. The trajectory doesn't just stay stable, it improves with every mile. Tiny perturbations that should accumulate over time are instead dampened. Minor wobbles disappear. Curve drift is corrected before it becomes visible. This isn't just stability, it's self-correction without delay. And perhaps even more remarkable, this perfect course isn't abstract. It's tailored, pointed directly into Earth's orbital velocity, with synchronized motion so clean that some satellites began to show minor timing offsets when recalibrating against it. 3i Atlas wasn't just passing through, it was travelling with us, locked into the same orbital ribbon at the same speed, with no adjustments necessary. It moved like it had been here before, or like it had been waiting. And with every second it held that course, Earth's instruments recorded the same unbroken truth. Whatever this is, it's not drifting, it's arriving. By the time 3i Atlas settled into near-synchronous motion with Earth's orbital path, a new anomaly emerged, quietly, almost passively. Its surface temperature was dropping, not suddenly, not in spikes, but with a controlled, measured decline that didn't match any thermal profile typically associated with comets or interstellar debris. This wasn't the result of distance from the Sun or lack of solar exposure. On December 10th, the object remained well within a zone of intense solar irradiation, and yet its thermal output began to dip. High-orbit infrared telescopes detected the first change, a barely noticeable cooling layer beginning to spread across the object's sunlit side. Not uniform, not erratic, but in a symmetrical gradient, as if the surface were following an internal algorithm, not just reacting to space conditions. This went against every rule in the cometry playbook. Traditionally, objects this close to the Sun experience thermal acceleration. Ice sublimates, core pressure builds, and solar heating ramps up the release of jets and gas. But 3i Atlas wasn't flaring, it wasn't venting, and it definitely wasn't warming. Instead, it was behaving as though its heating cycle had ended, and a new phase had quietly begun. Cooling. Not all at once, but through rings of temperature decline, spreading slowly outward from the upper surface layers and tapering across the body with rhythmic timing. That detail was what tipped researchers off, because temperature loss in natural objects tends to be chaotic, determined by structure, density, orientation, and rotation. But this pattern wasn't chaotic, it was modular. Sensors tracked repeating intervals between bands of cooler material. Each layer held a consistent delta from the one beneath it, almost like armor plates shifting from active to passive mode, one at a time, and this opened a wave of speculation. Some proposed that the surface was covered in phase change materials, the kind that can absorb and store energy for later release. On Earth, these materials are used in aerospace shielding, advanced satellites, and next-generation computing systems. They allow structures to survive extreme heat by delaying thermal overload. Could 3i Atlas be using the same principle, but in reverse? Could it be intentionally lowering its thermal profile to blend in with space? Others considered a cloaking mechanism, less theatrical than science fiction, but grounded in real physics. In infrared camouflage theory, an object can emit just enough radiation to match its background, effectively vanishing from heat-sensitive tracking systems. It doesn't make something invisible, but it makes it harder to detect. Was this comet hiding, or simply conserving energy? Still others speculated that the cooling was related to the earlier formation of the solar windbow. Perhaps the same field that reflected high-energy particles was now drawing heat away from the surface, acting like a radiator venting accumulated thermal load into space. But whatever the mechanism, the timing raised eyebrows, because the cooling began precisely as 3i Atlas matched Earth's orbital velocity. It wasn't earlier, it wasn't later, it was synchronized, like a stage of descent, or arrival, or entry. The message, if one could be inferred, was subtle. The heating phase is over. Now we cool. Now we wait. And perhaps that final silence, the gentle, deliberate loss of surface heat, was not a sign of retreat. Perhaps it was preparation for the last phase, which hadn't happened yet, but was coming next. For a full 12 hours after 3 Atlas matched Earth's orbital path and began its silent cooling phase, every monitoring station on the planet shifted to maximum alert. All eyes, telescopes, satellites, deep space antennae were locked in. After the sudden radio pulse, after the precision trajectory, after the synchronized surface temperature drop, something had to be next. Something had to come. But instead, nothing did. No second signal, no new thermal spike, no shift in motion, trajectory, or tail behavior. Just stillness. 3i Atlas didn't slow down. It didn't speed up. It didn't rotate differently, or release a new jet or fragment, or exhibit any of the typical behaviors associated with comets nearing perihelion or close proximity to a planetary body. Instead, it became quiet again. Not inert, just eerily stable. The object's emissions across all bands flatlined into what researchers called passive background mode. The reflectivity levels remained fixed. The tail froze in a rigid arc, no longer changing structure or brightness. The spectral lines that had been shifting subtly over the past days now locked into place, as if frozen mid-motion. Even solar-wind interaction halted. The bow shock observed earlier had faded, not because the wind had changed, but because the object no longer reacted to it. It was as if it had decided to disengage from external forces altogether. To many, it felt like a door had closed. A transition had been completed. Whatever phase 3i Atlas had been progressing through, ignition, jet activity, tail expansion, alignment, seemed to end the moment it reached co-orbital proximity with Earth. The object didn't vanish, but it stopped interacting, and that silence was deafening. Radio telescopes scanned for any hint of another signal. Spectrographs monitored for any chemical changes. Infrared scopes tracked surface shifts down to microkelvin. But the data held steady. It was almost as if 3i Atlas had slipped into standby mode. Not dead, not drifting, but waiting. Like a machine that had completed a boot sequence and was now ready for the next command. Or perhaps ready to receive one. Some scientists likened the silence to a heartbeat stopping. Not in failure, but in anticipation. The kind of pause that comes not at the end, but right before the next beginning. Others took a more sobering view. If the earlier radio emission was a handshake, then this silence could be the waiting room. Not a pause for breath, but a signal of conclusion. As if 3i Atlas had delivered whatever message it carried, through its motion, its light, its cooling, and its alignment, and was now simply listening. Not to us, but for something we couldn't hear. Still others feared this was the final act, that nothing else would follow, that what we had witnessed was the entirety of its mission, and the silence now was residual, like the echo of a bell that had already rung. But there was one more detail. Just before it went completely still, just before the data streams leveled off, astronomers at the Mount Lemmon Infrared Observatory detected one final anomaly. A flicker. Tiny. Brief. Like a flash from deep inside the object. Just one. It wasn't bright. It didn't repeat. But it came from the center, not the surface, and it registered in wavelengths outside the usual thermal bands. Something far colder, far deeper, and then nothing. Which left everyone with the same unspoken question. Was that the end? Or the last confirmation that something inside 3i Atlas had now activated, and was watching back? No one knows what happens next. Not NASA, not ESA, not Avi Loeb. Because whatever 3i Atlas is, it just crossed a threshold. And now, the silence is not ignorance. It's intentional. Tell me in the comments where you're watching from, and what time it is right now. And don't forget to subscribe, because the next update could change everything. We'll be watching, so stay ready and stay awake.